Modbus inherently handles 16-bit unsigned integers, specifically holding registers. Representing a 32-bit IEEE 754 floating point value requires two consecutive registers. The critical hurdle is not the register read itself, but the subsequent interpretation of those 4 bytes. A single 32-bit float consists of 4 bytes, S, E, M1, M2. Modbus specification does not mandate the order of these two 16-bit words, nor the byte order within those words. This ambiguity leads to 4 common, incompatible data formats deployed across industrial devices. Failing to correctly identify the device's specific Endianness configuration results in wildly inaccurate readings, often manifesting as extremely large or small denormalized numbers. We must systematically map the 4 possible byte sequences to the standard IEEE 754 structure to reliably extract the true floating point value. When requesting a 32-bit float starting at address N, the Modbus master receives data from register N and register N+1. Let R1 be the 16-bit value from register N, and R2 be the 16-bit value from register N+1. Each register R consists of 2 bytes, B high and B low. Standard Modbus uses Big Endian byte order within the 16-bit word, meaning B high is the most significant byte. The 4 raw bytes are R1 B high, R1 B low, R2 B high, R2 B low. The challenge is mapping these 4 bytes to the standard IEEE 754 sequence: byte 0, byte 1, byte 2, byte 3. Byte 0 is the most significant byte. The 4 variations arise from swapping the R1 and R2 word order and swapping the byte order within R1 and R2.
The IEEE 754 single precision float standard defines the 32 bits. Bit 31 is the sign bit. Bits 30 through 23 form the 8-bit exponent. Bits 22 through 0 are the 23-bit mantissa. When stored in memory following the standard Big Endian convention, the 4 bytes are ordered from most significant byte to least significant byte. Byte 0 contains the sign and the most significant part of the exponent. Byte 3 contains the least significant part of the mantissa. This standard sequence, B0, B1, B2, B3, is the target structure we must achieve, regardless of how the Modbus device transmits the data. Any deviation from this B0, B1, B2, B3 sequence requires byte manipulation before conversion. This configuration is often called Big Endian or 4321 format. It represents the most straightforward mapping. The device transmits the data such that the first register, R1, contains the 2 most significant bytes, B0, B1, and the second register, R2, contains the 2 least significant bytes, B2, B3. Furthermore, the bytes within R1 are ordered B0, then B1, and within R2 are ordered B2, then B3. The resulting 4-byte sequence read from the wire is B0, B1, B2, B3. When using programming libraries, this typically corresponds to the standard network byte order. If your system analyst tool supports direct Big Endian float conversion on the 4-byte buffer, this is the configuration to select. This variation maintains the standard word order, R1 followed by R2, but swaps the byte order within each 16-bit word. R1 now transmits B1, B0, and R2 transmits B3, B2. The resulting 4-byte sequence is B1, B0, B3, B2. This is sometimes referred to as the 2143 format. To reconstruct the standard B0, B1, B2, B3 sequence, the system must perform a byte swap on the first pair, B1, B0 becomes B0, B1, and a byte swap on the second pair, B3, B2 becomes B2, B3. This requires specific byte manipulation logic or utilizing library functions designed for 16-bit word byte swapping before the final 32-bit float conversion.
This configuration involves swapping the order of the 2 16-bit registers, R2 followed by R1, while maintaining Big Endian byte order within the words. R2, containing B2, B3, is transmitted first. R1, containing B0, B1, is transmitted second. The resulting 4-byte sequence is B2, B3, B0, B1. This is often called the 3412 format. To correct this, the system analyst must first read the 4 bytes into a buffer, then swap the first 2 bytes with the last 2 bytes. After this 16-bit word swap, the buffer contains B0, B1, B2, B3, ready for standard 32-bit float interpretation. This is a common configuration found in devices prioritizing register address simplicity over standard network byte order. This is the most complex variation, combining both word swapping and internal byte swapping. R2 is transmitted first, but its bytes are swapped, B3, B2. R1 is transmitted second, and its bytes are swapped, B1, B0. The resulting 4-byte sequence is B3, B2, B1, B0. This is the 4321 format applied in reverse, sometimes called the 1234 format. To reconstruct B0, B1, B2, B3, the system must first swap the words, resulting in B1, B0, B3, B2, and then swap the bytes within those words, resulting in B0, B1, B2, B3. Alternatively, a single reverse operation on the entire 4-byte sequence achieves the target B0, B1, B2, B3 structure. Regardless of the Modbus protocol used, RTU or TCP, the data acquisition layer must reliably extract the 4 raw bytes corresponding to the requested float. These 4 bytes must be placed sequentially into a 4-byte buffer. For example, if the Modbus library returns a list of 16-bit integers, R1 and R2, the system analyst must explicitly serialize these into the byte buffer based on the library's internal byte ordering for 16-bit integers. If the library returns raw bytes, ensure the sequence matches the order received on the wire. Once the 4-byte buffer is populated, the system analyst applies the necessary permutation, the swap operation, based on the identified Endianness configuration before passing the buffer to the IEEE 754 conversion routine.
Python's Struct module provides a robust mechanism for handling these conversions efficiently. The format string dictates both the size and the Endianness. For the standard Big Endian, B0, B1, B2, B3, use the greater than symbol followed by F, like greater than F. For the swapped word Big Endian, B2, B3, B0, B1, you must first rearrange the buffer bytes before applying greater than F. For the swapped word Little Endian, B3, B2, B1, B0, reversing the buffer and then using the less than symbol followed by F, less than F, might work depending on the initial buffer construction. The key is pre-processing the raw 4 bytes into the standard Big Endian sequence B0, B1, B2, B3, then using greater than F, or into the standard Little Endian sequence B3, B2, B1, B0, then using less than F. When connecting to an unknown device, use a known test value, such as 123.45, written to the Modbus register pair. Read the resulting 4 raw bytes, BA, BB, BC, BD. Convert these 4 bytes into their hexadecimal representation. Compare this sequence against the 4 standard permutations of the IEEE 754 representation of 123.45. For example, if 123.45 is represented as 42F6E666 in standard Big Endian, check if the received sequence matches 42F6E666, which is standard Big Endian, or E66642F6, which is swapped word Big Endian, or F64266E6, which is Big Endian Word Little Endian Byte, or 66E6F642, which is swapped word Little Endian. This systematic comparison immediately identifies the required permutation for the system analyst's parser implementation.